Now that doesn't make any sense because there's at least 180 configurations because there's 180 degrees you can be in, right? So that means I'd get 180th fraction of the whole light. That isn't 50%. 1 over 2 is 50%. 1 over 180, that is not 50%. So let's prove, because at first, right, I was like, well, what's happening is this vertical polarizer will just let in 45 degrees to the left and 45 degrees to the right, where it's red, you know what I'm saying? And it just makes it through, and they're just telling us that it's, vertical, and they're lying, you know what I mean? So I had to prove that they were not lying, and this is the proof right here, okay? Let's say this is the first filter right here, right? So you let in all this red stuff, all those configurations, right? When you take it into a second polarizer, right? Let's say you took it into a polarizer that was horizontal, right? That means the blue would be the red part, right? And you have all these the red configurations trying to go into the blue configurations. You can see they don't overlap. You would have zero light. So it almost sounds like they're right. But then when you use, say, a 22.5, instead of rotating at 90 degrees, you rotate it just 22.5 degrees. Now things don't work out that way. If this was the first filter and it let in all these configurations because they were close enough, right? When you put it through this filter, right, you can see the red part is the same. So it's 45 degrees left and right to this 22.5 degree thing instead of this 0 degree thing, right? So you have shifted that red, how you can get in, the hole, you have shifted it 22.5 degrees, right? That means this, see where the orange arrow is, right, that empty space. Over here you have light coming to the hole, but there's no hole there you can see. It's white, right? And so only 1, 2, 3, these next 3 slots, 1, 2, 3, can actually get into the, through this filter, right? So there's 4 paths, but you can only make 3 of them. That's 75%, right? But if we look over here and do the math, we know, and we do experiments, we know 85.4% gets through, not 75, okay? Now once you look at these other arrows here, this arrow here and this arrow, that's an opening that the light can come into, right? But there's no light there. We can see there's no red part over here that can get through there, okay? So this proves they're not just coming through and they're, slightly off askew, you know what I mean? They're taking all this red part, all those red configurations, and they're just lying, saying it's vertical when it comes out. No, they're telling the truth. This proves it right here. I know I'm trying not to repeat myself and be repetitious, but I have to at least go over this little bit here again, because that's what everything is based on. That's what this whole thing is about, is these polarizers are just basically antennas. Okay, yes, they have one extra function, that an antenna doesn't have. But let's go. I have to go over the the antenna again. Here's your antenna. It's just a piece of metal, right? If you hook up some AC to it, right, some alternating current, so that the the current goes back and forth, back and forth, back and forth, right? That makes the electron go back and forth. That accelerates the electron, and accelerated electrons do what? They throw out photons. And what's a radio wave? A photon. So look at that. It comes out, right? This right here, boom, boom, boom. And what I want you to realize is the electron's going up and down, right? The light that comes out, yeah, it oscillates in the same exact way. If the electron's going up and down, then this electric field on this photon, right, this radio wave, is going in this up and down in the same way, right? When it hits this piece of metal, right, the other antenna, it absorbs, the antenna absorbs the photon, and it starts oscillating, right? And then that oscillation makes it throw out a photon, right? And it's going to throw it out back the way it came, right? I mean, technically it throws it out in a sphere, but it's not like light when you have like a light bulb, you know what I mean? It's actually, a lot of it comes out in a plane. But anyways, that's neither here nor there. The point is that this first electron, he started oscillating like this. That means they all did it. This photon did it, this electron did it, and this other photon that got thrown out. They all are oscillating in the same way, up and down, up and down, up and down. Okay? So this electron here absorbs the photon and oscillates, and the energy goes to that oscillation, right, as heat loss, or it goes to re-radiating or re-emitting the photon. Right here you can see it. But remember what I said, they go up and down, they oscillate, everything oscillates, you know, the way the first person oscillated, which would be this electron. Radio waves are photons, right? And they are polarized. Okay, why? Because most antennas are polarizers. You know what I mean? So they polarize. That's what polarizers do to light. And radio waves are light, right? Now we're going to go into something called the polarization loss factor. Okay, and that's something that a antenna has. An antenna. Yeah, you notice my new toy. I got a whole bunch of physics toys. So I'm going to be doing some experiments. I got polarizers, a bunch of lasers, and a whole bunch of slits, things, and all kinds of stuff. But anyways, but before we go into the polarizer loss factor for antennas, let's talk about this thing over here called antenna coupling, okay? Because an antenna is a polarizer, okay? So look at this first example. You got two antennas, right? Remember how when we had our polarizer film, right, or little plastic sheet, right? You have two of them in there, have 0 degrees in between them. They're both vertically oriented. How much did you get? You got 100%. Well, guess what? These antennas do too. In the same way, with 90 degrees, you get 0. 45%, you get 45 degrees, you get 50%. Just like over here. Over here, this is all for what we had last time on the polarizers that were plastic or whatever, you know. Same here, 22.5 degrees, 30 degrees, 80 degrees. Yeah, all these percentages, they're the same. They're all the same. Do you know why? Oh my God, because they're polarizers. Okay, antenna coupling is basically, since they're polarizers, and you know how a polarizer works now, right? If you have it at 0 degrees, like here, you know, you're going to get all of it. The more you move it down like that, and then to that, and to that, and to that, you know, then you get down to 90, boom, you have 0%. Same way with an antenna, okay? This, that's why they call it antenna coupling, right? And the same rules apply. Like, you know, you can have the vertical one, you know, the three polarizer paradox. You can have that same paradox here. You get the same math and the same everything, but nobody calls it a paradox when we're talking about antennas for a radio. But somehow, even though it's the same exact thing, when it's when it's a polarizer that's an antenna for radio, that it's okay. It's not magic. But you know what? Hey, when it's plastic, it is magic. Why? Why is it magic when it's plastic, and when it's not plastic, it's not magic. It's not mystery. Alright, I hope you can see this. I'm not going to close this because they won't give me an X to exit out, and I'm not hitting any of these buttons. But here's a thing called an article, the polarization loss factor in antenna communications. Whenever there is a mismatch, a polarization mismatch in antennas, EM power is lost. Lost EM power can result in faulty transmissions and poor signal reception, meaning poor, you're not getting the photons, you're not getting the radio waves, you're not getting the photons. The loss of EM power due to a polarization mismatch is defined by the polarization loss factor, PLF. Polarization is an essential concept in antenna-to-antenna communication according to the shape traced by the electric field vector. Polarization can be classified in three different ways: linear, circular, and elliptical. Signal reception is damaged if it's not as good if the polarization of the antennas does not match any polarization mismatch. Signal reception is damaged if the polarization of the antenna does not match. Any polarization mismatch is characterized using the polarization loss factor. When transmitting and receiving antennas are of different polarizations, for example with horizontal and vertical polarization respectively, then the angle between the radiated field is 90 degrees and no power is transferred between the antennas. Yeah, does that remind you of something? PLF is the measure of power that is not captured from the incident wave by the antenna. Okay, it can also be described as a multiplier that defines what fraction of the incident power is captured by the receiving antenna, meaning how much is getting through your to your antenna, your intensity. A reduction of power received by the antenna is given by the PLF. Keep in mind these things in parentheses, those are just steps. That's not part of the equations he's talking about. In the case of linearly polarized antennas with an angle between radiated electric fields equal to, look, cosine theta squared. That 5 is just a step. That's not part of the equation. He's saying the polarization loss factor is cosine theta squared. That's what ours is. Remember, intensity. What's the loss? We always multiply it by cosine theta squared. You know why? Because they're both antennas and they're both polarizers. That's why. Antennas are sensitive to polarization. Without polarization matching, proper transmission and signal reception are hindered. You can use the PLF equations above, right, to calculate any EM loss caused by polarization mismatch. Quality antenna communication will require engineers to orient the antennas so that the angles between the radiated electric fields is nearly zero, just like we do with our polarizers, because that's what two antennas are. They're polarizers. And you have 100%. You don't, less, more cosine you have, the more you're gonna, not the intensity of that radio wave and photons is not going to be good. Antenna radio. The orientation and physical structure of an antenna determine the polarization of the electric field of the radio wave transmitted by it, meaning the photon it transmitted by it. For instance, an antenna composed of a linear conductor, such as a dipole or a whip antenna, oriented vertically, right? If you have your polarizer vertically, meaning your antenna, you will result in vertical polarization. Gee, and it's the same percentages too. That if turned on its side, the same antenna's polarization will be horizontal, just like when you have your plastic polarizer. You turn it 90 degrees. Guess what? You made it a horizontal. The linearly polarized antenna receives linearly polarized radiation at a relative angle of theta, then there will be a power loss of cosine squared theta, cosine theta squared.